one?
I mean, you can just give us all.
I bet it's the module. Yeah, I think it is. Stink. I did that in calc too. Yep. Look. Beep. Whoops.
So what are you gonna pop that sweet corn on?
Yeah, I don't know. Whenever I get hungry later today, I'm like.
Hey, also the CCP grades have been updated. Okay, with the Chapter 9 test. You'll notice that the only things still left in the spreadsheet are Chapter 10 test, Chapter 10 homework, and then the final exam. That's it. And then the blank stuff. All right, so let's get into it. Section 10.2, the last section. Independence. Remember, we learned a long time ago about independence, right? We previously learned that two events are independent if the occurrence of one event does not affect the probability of the other event. That's our generic definition for independence, right? You know what we can do, though? We can use contingency tables, which are basically like frequency tables. We can use what are called contingency tables to answer the question whether or not two variables are independent or not. Now, we are going to do this whole lesson based on this contingency table. Okay? Based on this contingency table. Now, it says an RXC. That just means R by C, row by column. That's going to be replacement numbers. A 2 by 5, a 3 by 4, a 5 by 5. An R by C contingency table shows the observed frequencies for two variables. The observed frequencies are arranged in R rows and C columns. So in this case, this is a 2 by 5 contingency table, right? The intersection of row and column is called a cell. It's kind of like a matrix, right? So say we had this grade distribution, this grade breakdown. We've never had this. Say we had this grade breakdown, and we had these 5. I would copy down this table because we are going to use this table throughout the lesson. Okay? We are only going to do one example throughout the lesson. So this is an example called a contingency table. I've got it distributed into males and females and grades, F, D, C, B, and A. Okay. Now, what I can do with this contingency table is to make the decision, are males and females grades independent of one another? Is grade independent of gender, basically, right? Is grade independent of male versus female? Okay. That's what we can say with the contingency table. And that's what we will be able to decide later on. Are these things independent or are they dependent? Right? Are they independent and dependent? Remember, back when we were using probability, we had the conditional rule for probability, right? We had if A given B is the same probability as the probability of A, right? If the probability of A given B doesn't change when I just take the probability of A, then those events were independent of one another. B did not have any effect on A. That's the probability rule for independence. What we're going to be using is hypothesis testing for independence. Okay, based on an example, based on a survey, right? Assuming two variables are independent, we can use the contingency table to find the expected frequency for each cell. If they were truly independent, these would be the expected frequencies for each cell. Now, how do we calculate that? This is the calculation for expected frequency. The same E is the same thing as yesterday. Remember how we had O minus E over E? Same thing's going to happen here. Observed minus expected over expected. This is expected. But instead of just having like one frequency, right, we're talking about two different variables having the frequency. So instead of just one column, we're going to have a whole chart worth of E's. A whole chart worth of expected. So that's why you see ERC is the subscript. Okay, so this would be like the expected frequency of male A, the expected frequency of female D, the expected frequency of male F, right? How to find those? You take sum of the row times sum of the column of that cell. You find the sum of the row, sum of the column, you multiply them together, and then you divide by the entire sample size. You divide by the entire sample size. You take sum of row times sum of column divided by full sample size. Okay, sum of row times sum of column divided by full sample size. So let's do it. Assuming the gender or grades are independent, calculate the expected frequencies for each cell in the contingency table. Now, to calculate expected frequency, I need my totals, right? Sum of row times sum of column divided by total. Okay, I need some totals here. Let's figure out my totals. Okay, what's my total F's? 25. Total D's?
31.
Total C's? 71. Total B's?
52.
Total A's? Okay, total males. No. Okay, 26 plus 20 is 46, plus 8 is 54, plus 20 is 74, plus 100. Oh, 100 on the dot. Okay. I'm guessing this is, I wonder if it's 100. This is 30, so 73 plus 73. Wait a second. Wait, this is 30. Yeah. Oh, it's 150. Yeah, it's way bigger. 150. I got it right here. What am I calculating for? So 250 here, right? Grand total 250. So now that I have some totals, I can find the expected. Now, if this chart is going to give me the expected, what do you think the given chart was? These are all the observed. Okay. Say I took my frequencies of grades versus gender, and it broke it down. This is what was to be expected if I had 100 males, 25 Fs out of a 250, right? This is male F. D, C, B, A, right? Okay, male F. Row, 100, column, 25. So I'm going to take 100 times 25, and I'm going to divide that by 250. What should I have expected in this cell? 10. Knowing that I had 100 males and 25 Fs total, I should have expected, out of 250, I should have expected 10. I got pretty close to that, right? Let's do that for each cell. Okay, so now let's do male D. 100 times 31 divided by 250. That's going to get me 12.4. And yeah, it's okay to have decimals. These are expected frequencies, not necessarily talking about actual people. All right, we got 71 times 100 divided by 250. That's going to get me 28.4. We've got B's, 5,200 divided by 250. That's going to get me 20.8. And then male A expectation is 7,100 divided by 250, which is at 28.4. Now let's do that whole same thing for the second row. All right, so 25 times 150 divided by 250. I should have expected 15. All right, 31 times 150 divided by 250. Oh, that's 15. 31 times, oh, that would have been 18.6 then. Yeah, I can just move the decimal. 18.6. I can do 71 times 250. Oh, shoot. 71 times 150 divided by 250. 42.6. 52 times 150 divided by 250. I did it again. Darn it. All right, move the decimal. 31.2. And then lastly, 71. Double check that one. Okay, good. 71 times 250. Oh, I did it again. Darn it. 71 times 150 divided by 250. Trying to go too fast. 42.6.
Survivor.
User.
If we just solve for the males, because they all add up to the final, could we just find the difference? Or...
I guess you're right. Yeah. What he's saying is, okay, I knew these add up to 25, right? If I got 10, I know the other one's 15. These add up to 31, right? So if I get 12.4, I just take 31 minus 12.4, and it's 18.6. Yeah, I guess you do that. Point. That's assuming that you got this row right. You know what I mean?
Right.
Like if you screwed up with the male, then ooh. All right, so those are my O's and my E's, right? This is the expectation, and remember, the expectation comes from how many total C's we had. Like this female C right there, 43. This comes from total C's I had, total females I had, total students I had, right? 71 times 150 over 250, that gets me to 42.6. That's the expectation that I should have gotten. Okay, now what we can do is run a chi-square test for independence. Now, it's going to be using the exact same chart, the chi-square chart. Okay? You're going to be using that exact same chi-square chart. But this, instead of a goodness of fit test, is called the independence test. A chi-square independence test is used to test the independence of two variables. Using the chi-square test, you can determine whether the occurrence of one variable affects the probability of the other of the occurrence of the other variable. Okay, and now think about it this way: when we were running that conditional test for independence, that was like absolute independence. This is saying, okay, if it's close, how close is enough that we could just say, yeah, that then they're independent, right? How close is close enough that yeah, I guess these things are generally independent from one another, right? They might not be purely independent, that's what was the conditional probability. Probability of A given B was probability of A. That's absolute independence. This is more, okay, they're close enough to the values because the expecteds, we got pretty close each cell, didn't we? Pretty close. So the expected values came out really, really, really close in terms of, generalities here. I know we're a couple units off here for our A's, but in generalities, we're pretty close. So how close is close enough? Well, the following conditions must be met, and that's what we can use the chi-square independence test for. Following conditions must be met. The observed frequencies must be obtained using a random sample. Each expected frequency must be greater than or equal to 5. That's the exact same thing for my chi-square goodness of fit test, right? It's the exact same thing, right? I had to have expected frequencies come out to be bigger than 5, and it had to have been obtained by using some sort of random sample, right? And again, I'm going to meet these conditions for everyone. Every time we do this, these conditions will be met. Now, how do we find our test statistic? Well, that looks familiar. The chi-squared test statistic is still the exact same thing. O minus E squared over E. O minus E squared over E. But the only difference is, yesterday we were working with just a frequency chart, right? Just a frequency table. Now this is a whole contingency, whole, basically matrix of values rather than just like a table, okay? Now, I do need a degrees of freedom. Take a look at the calculation for the degrees of freedom. It's R minus 1 times C minus 1. Number of rows minus 1 times number of columns minus 1. That's going to get us our degrees of freedom. That is going to get us our degrees of freedom. It's not just, row minus 1. It's not just column minus 1. It's not. Yesterday it was K minus 1, number of categories minus 1. Here, it's total number of cells minus 1. Take a look at it. Like, how many responses total did I get? I had 2, 4, 6, 8, 10, right? So the calculation for degrees of freedom is rows minus 1 times columns minus 1. Total number of cells was row times column, right? So what we're doing here for our degrees of freedom is row minus 1 times column minus 1. So instead of just straight up taking row times column to figure out cells, you just take row minus 1 times column minus 1. Okay. And again, O represents the observed frequency and E represents the expected frequency. All right, so now let's run a hypothesis test. Now, just like in section 10.1, just like the goodness of fit test, the hypotheses are going to remain exactly the same no matter what problem we have. You know, the goodness of fit test said, okay, the distribution is as shown for our null, and then the alternative is the distribution is not as shown. For the independence test, well, the variables are independent is my null. The variables are dependent for my alternative. You know, it was kind of easy to figure out the null and alternative for the goodness of fit test because it was, remember, the equality was the null, right? The equality was the null. The distribution is as shown, the distribution is equal, was my null. Here, I don't know, I kind of feel like these are backward because if they are dependent, don't you think they are equal? Oh no, I guess no. I'm thinking about that wrong. For they to truly be independent, the distribution for my expecteds should be the same as the distribution for my observed, right? So therefore, I guess that would be equal to. Yeah, this is an equal to statement. The distribution for my O's is equivalent to the distribution to my E's. So there's my equivalency. I was thinking about it wrong there. So the null hypothesis is always going to be the variables are independent. The alternative hypothesis is therefore that the variables are dependent. So again, the only thing that we could ever possibly do is reject the fact that the variables are independent, therefore making the variables are dependent. Can I ever say definitively that the variables are independent? No, I am just saying that they are not dependent, right? That they are not independent, so therefore they would be dependent. All right. This is always going to be right-tailed test. So when you're doing hypothesis testing, just like for the goodness of fit test, you're always going to be checking if your chi-squared is greater than your chi-squared critical value, right? It's always going to be greater than. And I think some of us are confusing that a little bit. Some of us are missing that because I was from grading the chapter 9 test. We're confusing, okay, what is our test statistic? And is our test statistic supposed to be greater than, less than, or equal to? What is it supposed to be? If it's a right-tailed test, your test statistic has to be greater than your critical value to reject. If it's a left-tailed test, these are not left-tailed, but if it were to be a left-tailed test, then your test statistic would be less than the critical value. And if it's two-tailed, well, then your test statistic could be either greater or less than your critical values. Getting a little haircut. Okay. So let's run a hypothesis test based on this. Okay, let's run a hypothesis test. Now, I am going to copy over, so we don't have to do it again. I'm going to copy over all of this info. Oh, sorry. Whoops. Zip. Zap. We're going to, current page, sure. Come on. Respond. There it goes. Okay, so I'm just going to drag this over here. Oh, there it is. It's giant. Okay, I'm going to delete this table. Okay. So here is, I'm going to make this just a little bit smaller. Here's our O minus E. Or here's our O's and our E's, right? Let's perform the hypothesis test. What do we always do at first in a hypothesis test? State the null, state the alternative. Well, that's super easy with an independence test. The null hypothesis is that the variables are independent. That means the alternative is the variables are dependent. let's start off by finding our rejection region. This is going to take me a while to do my test statistic. Let's find my rejection region. Here is my rejection region. Now, remember, I'm using alpha 0.05. What is my degrees of freedom? How many rows do I have? 2. Minus 1 is? How many columns do I have? 5. Minus 1 is? 1 times 4 is? So I have 4 degrees of freedom. So I would go to my chi-square distribution. I lost my chi-squares. Oh, there. So I look for degrees of freedom 4, alpha 0.05, 9.488, is that what you said? 9.488. So our critical value is 9.488. So our rejection region is that if chi-square comes out to be greater than 9.488, I can reject the null. Basically, think about this. If the sum of all my O minus C squares over E turn out to be greater than that, then there's too much spread in the data. There's too much difference between O and E, so therefore I cannot say that the variables are independent. I have to reject that statement. Okay? So that's why it's always going to be graded in. Always going to be graded in. It's always going to be a right tail. Let's figure out chi-square, shall we? Now, for a contingency table, we basically have to make a third table. We have to make our O minus E squared over E table now. Okay, we have to make a third table now. Let's do that. We got male, female, A, B, C, D, F. So let's calculate my O minus E over E, O minus E squared over E. Okay, we got 10 cells to do. Follow along. O, 11, minus 10, squared, that's 1, over E, 10. 0.1.
You have that in the F.
What's that? Honestly, at that point, does it matter? No. Because I'm just going to be summing them all up, right? You're totally right. I did screw that up. But at this point, these are just values. These are just spread values, right? How much does O differ from E? And in the end, I'm just going to add them all up. Okay, 15 minus 12.4 squared divided by 12.4. 0.55. I'll round it to the nearest hundred. Okay, let's look at male C. 28 minus 28.4 squared divided by 28.4. 0.01. Almost negligible. Okay, we're going good. We want these values to be small if, well, I guess it depends on what my angle is, whether it's independent or dependent. If I'm gonna reject my null, these values need to get bigger. If I want to fail to reject it, then these values need to stay small. All right, 20 minus 20.8 squared divided by 20.8. And that gets me 0.03. And let's look at male A. 26 minus 28.4. 26 minus 28.4 squared divided by 28.4. Okay, 0.20. Okay, let's do the row 2. 14 minus 15, that's 1. Squared is 1 divided by 15. 1/15 is 0.07. Female D. 16 minus 18.6 squared divided by 18.6. 1/3, 0.36. We got 43 minus 42.6 squared divided by 42.6. That's really small. 0.0, ooh, negligible, 0.00. Female B. We got 32 minus 31.2. Oh, that's log. Answer squared. Oops. Divided by 31.2. Again, another small. 0.02. And then the last one here, 45 minus 42.6 squared divided by 42.6, which gets me 0.14. All right, let's calculate the sum.
There's no way.
Doesn't look like it, right?
1.48.
1.48? Thank you. Okay, is chi-square greater than 9.488? No. So what's our decision? Fail to reject. Okay. Fail to reject the no. Is that necessarily saying that these must be independent? No, I just can't say that they're not independent, right? So we say there's not enough information to reject that they are independent, that the variables are independent. Make sense? So that's how you run a hypothesis test for independence. Okay, that's how you run a hypothesis test for independence. It's great fun. Last homework